In this section, we're going to look at the case where you have a specific range you want to keep to, and you want to figure out the sample size necessary to stay within that range. So there are some cases where, as the researcher, you may know the specific tolerance or margin of error that you need to keep your confidence interval to, but you don't know the sample size that you need to take to achieve that tolerance. So we have an equation that we can use to estimate the sample size required to stay within a certain margin of error. That equation is found by n equals z squared times p hat times 1 minus p hat divided by e squared. So as a reminder, E stands for the margin of error. So let's look at an example. Another research team is interested in estimating the proportion of teens that text while driving. They decide they want to calculate an estimate that's within 3% of the actual proportion or actual percentage. What is the necessary sample size needed to create this estimate? Now, one very important piece of information that I'm missing here that we need to calculate the necessary sample size is that they've decided that they're going to do a 90% confidence interval. We do need that piece of information. We are also missing what is the sample proportion, but if we knew the sample proportion, then we would know the sample size. So what we can do is we can use 0.5 when we are calculating the sample size if it's not otherwise stated. And we use 0.5 because it's halfway between 0% and 100%. And it just gives us a good middle ground. And when you do all the calculations that are necessary, it's going to give us the biggest sample size necessary. Any of the other possible values that we could use for p hat would result in a smaller sample size. By using 0.5 as p hat, we're ensuring the largest sample size requirement, and that's always better to have a bigger sample size than a smaller sample size. So since we don't have anything in here that says, oh, you can go ahead and use 0.8 as your p hat, we're going to go ahead and use 0.5. So with this formula, we have a 90% confidence interval. P hat is 0.5. Our margin of error is going to be 3%. We can see that right here within 3%. And that's really all we need. So we do need to find the z-score, and we find the z-score the same way we would find the z-crit. This is the same z-crit value. So if it's a 90% confidence interval, that means our alpha is 10%. So alpha over 2 is 5%. So in Excel, I'm going to do norm.s.inverse of 0.05. Alpha is 100 minus 90, and then we divide that by 2, and that's what we plug in to norm.s.inverse. When we do that, we get negative 1.645, and we always ignore the negative with these confidence intervals, even for sample size. We don't want to have a negative sample size. If we use the negative, we're going to get a negative sample size. That would not make sense. So this is our z-score, 1.645. So the sample size is going to be 1.645 squared times our best guess for p hat would be 0.5 times 1 minus 0.5 divided by 3% as a decimal is 0.03 squared. 1.645 squared times 0.5 times 1 minus 0.5 divided by 0.03 squared. If you type it in exactly as it's written with the parentheses where they need to go, don't add any extras, don't remove any parentheses, you can do this all at once in your calculator. You don't have to break it into pieces. And you should get 751.67. We're going to round up to 752 because we cannot sample a portion of an individual. And we're talking about teenagers, so we have to sample a whole teenager. We always want to round up on these because we want to have a bigger sample size as opposed to a smaller sample size. Bigger is better in terms of sample size. So even if this was 751.2, I would round up, not down. So if they want to be within 3% of the actual value, and we start off with a sample proportion of 0.5, then they need to take a sample size of at least 752 to have a margin of error that small. And that's how we estimate the required sample size for a confidence interval.